Hello. Good morning. Oh, all right. We are here with Solomon's Club. I am super annoyed. They used kanji for kurabu. Okay, this is my second time using this emulator. I have learned it as best I could in one day for you all. But yeah, I don't super know how to start this, but if you have questions, feel free to ask. So I will pin that. Failed to pin? What does that even mean? There we go. All right, all right. All right, let's get started. Um, so, uh, oh, whoops, you're hearing it through my headset. Oh no. I gotta stop doing that. All right. Now you can hear. That might still be too loud though. We don't care about the sound that much. Okay. Welcome to game. So, I want to start with something a little stupid, just to show you what a typical cheat hunting would look like. Unfortunately, I did go through this game a bit, and this doesn't really work in this emulator for this game for the values that we actually care about cheating with, so we're going to do it with one that we don't. But one of the typical things that you want to use in I keep doing that is in this thing it's called RAM search. In other tools it's often called like a trainer, a memory trainer, cheat finder, things like that. This is a super common tool for finding cheats because it's pretty simple to use, and it sort of like it keeps track of all the memory that the game yeah, and then we can it keeps track of it over time, so we can compare the values over time and then find specific values based on the values that we can see on screen. So for instance, if we look up here, we're changing the room number pretty easily. Hi, Mr. Frisk. McFrisk. I keep doing that. I'm sorry. Yeah. Okay, so the room number is really easy to change, so we're going to start with that. If we start with doing a constant here, constant refers to a constant value. So basically, you're inputting a number into here. It won't matter for this because we're doing very small numbers, but this is hexadecimal input. So yeah, it says room 1 on screen here. So we're going to go ahead and put a 1 in the constant. Then we hit search. This is our initial search. We can see a bunch of things are changing rapidly. We don't want those, so we can go to back to old value here. Now this compares the current value with the old value. So you can see here in this column here that says value. This is the old. This is the current value, and then old value is the value that we found when we searched. So we can go ahead and say equal, and it filters out those ones that are constantly changing. We don't care about those. Now we go back to the game and actually change the value. So we go to room 2 and look in this list. But nothing changed. Oh no, right? That's okay. What this tends to mean is, well, there's two options. We'll get into the other option later, but with this option, first option here, what this means is what's commonly referred to as an off by 1 error. Not really an error in this case, but for our purposes, off by 1 error. What that means from a hacking perspective is that probably what we're looking for is not the actual value that's shown on screen, but something that's slightly different, right? In this case, we can look at what the actual values are available to us, 1 to 10, and say, well, most things in computer science are 0 indexed. They start at 0 rather than 1. So we'll say, maybe this is a 0. We can reset the search and try again. Constant, look for zeros, search. Things are probably changing in here, so we can just go ahead and do another of those. And then go ahead and switch. So we know what the new value is supposed to be. We can search for a 1. And we have two options here. Now, let's change this again. You can see the current values are changing, incrementing by 1 like we would expect. So they both seem viable for what we want for the room number. But if we go down, only one of them goes to 5. So 1 seems to be like the X position of the cursor, and then 1 is the actual room value here. And we can easily check that, right? So if we right click, we can say select in memory editor. This opens the memory editor for Emulicious. And then I believe it's, yeah, you have to scroll down once to get there. So we have 101 here. This is the one that's looks like the actual room number, right? So if we freeze this value at 2, we can move around and see that the room number at the top of the screen right here, that's not changing. So we've successfully found the room number indicator right here at C101. That's more or less how a trainer works. I'll show you again once we get in game. Yeah. Cheat Engine is also a memory trainer. Well, it obviously does more than that, but the original purpose was a memory trainer. Or I guess you could say the first screen you see when you open it up. Now, I'll unfreeze this. Now let's go into level 1. pause the game. So the first thing that I want to look for is the time. That's constantly going down. It theoretically should be fairly easy to find. Um, but I already spoiled it. It is not easy to find. So we'll go through this trainer process to show you, and then deal with it later. Now, the time value here is kind of a big number, right? 7,870. What this means in computers is you have to think about the max value for bytes, right? So everything in computers is represented by a byte. That is 8 bits. And the max value for 8 bits, we can go 1, 2, 3, 4, 5, 6, 7, 8. You can see the max value for 8 bits is 255. I probably should have increased the size of this. I hope it's visible. So anything that is bigger than 255, and you can say 256, assuming off by 1 again. Anything that's bigger than that is definitely going to be more than 1 byte. So now if we look at what the size of 2 bytes, FF is the same as what I just did, the full thing is once. So a byte is 2 hexadecimal digits. So the size of 2 bytes is this. So 7870 is less than this number at least. So we can say, yeah, it's probably 2 bytes, right? It started at 8,000. It can't go higher than that. They wouldn't need to do anything special with that. And the Game Boy CPU is more or less 8 bits, right? So we go in here and we say size 2, and that's in bytes. The type here we have signed or unsigned. It could be either. We don't know because 8,000 is below the signed max, which is this is the signed max. We'll get into why a bit later because it does come up. But for now, just know, I guess. It's not really that important right now, but we'll go with unsigned because that's safer, I guess. I feel like it's safer. So we don't have anything to search for at the moment. So we'll just go ahead and reset. We can say equals it eliminated 2 addresses, no big deal. So now what we're going to do is we're going to select less than. So what this comparison does is it says the current value, select any of these memory addresses where the current value is less than the old value. Since the timer is constantly decreasing, it should be less than the old value. Okay, now let's go ahead and play a little bit, move around, do some things, kill this guy, and hit search. Down to 95. Do some more. Open a door. We're down pretty low here. We can see there's 11 left, right? But none of them are decreasing anymore. There's these 2 that are hopping around, but that's not what we're looking for. We're looking for something that's constantly decreasing. None of these are the case. Since we did a full relative search, we can be pretty sure that the time isn't actually in the memory that this RAM search is looking at. I kind of hate that that's the case, but it is the case. And for Game Boy, specifically what that means, there's there's multiple segments of RAM in the Game Boy. Shows you right here we have RAM, which is what it was searching. That's the regular RAM, what you would think of in a computer as well. The VRAM, which is the video RAM. We don't care about that. That's for drawing the screen. And then we have the HRAM, which is the high RAM. This is a special RAM location that's at FF in the high byte here. It's I was looking into what it is exactly. It doesn't seem to be faster or anything. It's just different. It's in a different location, and for whatever reason, Emulicious's tool doesn't search it. So what we can presume is that it's here, but we don't know where it is in here, right? So we're going to use a different method for finding the time. There's a lot of methods for finding cheats and other information in this field. And what we're going to look at next whoa, okay, there we go. What we're going to look at next is this. This is the tile map. So this shows you all the tiles that are currently on screen. It shows you ones that are off screen as well, because this has like a window that it can move. If we open the menu, we could see that scroll over, and we'll do that later. But right now what we're focused on is these time tiles. What we're going to do is say this tile right here, the 4, it's changing the fastest. We'll look at that one, right? So you click the tile, like I just did, it puts this little box around it. And we can look down here, and it says source tile index. It tells you where, what set it, and where from. If it says unknown here, I forgot to go through this, but if it says unknown here, which it would when you just started, you have to go into Memory Tracer and click this enabled button, and that will start recording all the addresses for you. So, oops, we see FFC5 here. So we can go down into FFC5. Is that FFC5? Can't count. No, this one's FFC5. We can see that right there, 74. So this doesn't mean a lot looking at it, you would think initially. However, it does actually. You can see a hint here, the tile index. It says 174, but it is in fact 74. There we go. So you look here, 372, 74 in hex. This is the tile that's currently displayed in that location. So this value here, the 74, is the tile index for the 10s digit time tile on screen. What we can do now is say, well, hey, we know that's the tile we want. What is actually writing to it? So to do that, we toggle on a watch point. Open up the watch point properties real quick and say, this is our watch point here. We want to see what writes to it, so we'll remove the read check. We don't care about what reads from it. Probably what reads from it is what just draws to the screen, right? So now that we have that set, we'll continue the game in order to see where that breaks. Let me just, okay. Unsurprisingly, it breaks immediately because it's, was moving that rapidly before. Now, what we're looking at here is actual code. Um, uh, okay, so this is assembler code. I will explain what everything means if it's relevant. Feel free to ask about other things. I am happy to answer. I don't have the document up, but I can bring it up. It is assembly, yeah. So this is it tells you, where does it tell you? Was it here? Yeah. RGBDS style assembler dialect, right? There's another one that I saw. Is that it? Different thing else? I don't know. I don't find it. Anyways, as I recall, the Game Boy is Z80 assembly. Don't quote me on that. It is a slightly customized version. I'll just open the doc. I'll have it. Processor. Let's see. Yep, similar to the Z80 processor. Yay. Okay. So this command that we're on, this is the one that actually did the write here. We can see that because it says this RAM FFC5 here. This is a label that Emulicious disassembler generated to refer to the position that we broke on. LDH is load high. So it refers to loading into the high memory location, the high RAM. A is the accumulator. It's a register, a CPU register. CPU registers are kind of like variables at the CPU level. There aren't that many of them, and they're the fastest kind of memory because they're like, in the processor, like really in it. Yeah, I don't know how to describe it. So we want to look at okay. So anyways, this instruction here then says load A into this memory location. So if we can hover over this, we can see what this means. RAM FFC5 shows you that label itself refers to FFC5, as one would expect. Then it shows you the @ symbol, which is the internal Emulicious expression syntax of doing it. And what that means is it's a dereference, right? So you're looking at the value that's at the address FFC5, which is 74, as we can see here as well. That's the same sort of thing that these brackets are doing in the assembly. It's saying move A into this memory location, as opposed to assigning it to a label like you would in a normal programming language, right? In C, it would be, if you know C, it would be like putting an asterisk before this RAM FFC5 label in an assignment. Now, so because the value that we wanted, that we care about, came from A, we now want to figure out, well, where did A come from, right? If it has a label here, that does mean that it can be jumped to, which you can see right here, or not there, right here. A lot of people are intimidated by assembly, but it's super straightforward. It's like, it's not easy by any means, no, but it's straightforward in that it's very simplistic, right? It's a language that rocks can understand. um, Basically, you have to maintain a state, right? The registers, the memory and stuff, but uh, everything else is just an instruction. It goes in linear order. There might be branching with these jumps and stuff, but it does exactly what it says on the tin, no more, no less. It can be difficult to interpret all that into something that makes sense to a human, but at the very base level, it's simplistic. And we'll go through that a little bit. So we can see here that so like this label and looks like it's just this label jumps to that. So there's that op. Hello? Hello. That's weird. How much did you miss? I have no idea why that happened. Uh, like 3 minutes? Shit. Okay. We'll go back to we'll go back to the address. Um, okay. So I don't know where we left off exactly what I was talking about, but we can talk about this again. So, um, so because A was assigned to this memory location, I hope you got all the explanation of pointers because I don't want to do that again. Since A is being set to this memory location here, we want to figure out what's setting to A. Okay, good. So what's setting to A? There's two options here. This could fall through here, or something could jump to this address. The only jump I see right here is right here. We can actually check that by going to the open reference hierarchy. Yeah, that's the only one. So if we look at those options, right? So in this case, A would be set from C, and in this case, A would be 0. A isn't 0, so A came from here, right? And we can consider, what came here, what C set to, that sort of stuff. We can see that there's these two options here. If we look at the open reference hierarchy, it's just those. So C was set probably by this call. We don't know. We don't have to dive into that just yet. But if we scroll up just a little bit, we can see that there's also this add 70 thing here, which sets the byte before it. So we got, what was this? FFC5. Oh, this is the fourth digit here. It always sets 70. So that's FFC5. And then here we set FFC4, FFC3, FFC2. And FFC2 is here, actually, which is a 0 currently. But it follows the same pattern, so we'll just accept it, right? This is the last one scrolling up, the last one that follows this pattern. So we can look at maybe what set this C, right? Now, if we scroll up here, the reasonable guess, right, is that call from before. It's the same one as from before. So let's go ahead and go to destination. If you have questions in common, please ask. I'm happy to answer. Um, Now in this function, scroll down to the ret real quick and see sort of where C came from. It does seem to affect C at least, so it's a good guess to come here. So what is C set from? It's not here, not here, not here, not here, not here. It wasn't here at all. Oh no. Okay, we'll go back. We can return to PC by hitting space. Scroll back up. I don't know if there's like a go back or anything. I haven't found it. Yep, that's the whole thing about like reverse engineering, right? You have to go backwards to where data came from. It's the long part of the process. Here we go. So if this didn't set C, it was this, right? This value here set C, and it went into this label and then manipulated it somehow. We don't really care. So we can tell that that was set from FFC1, which is the value before FFC2. It's this value right here. And this is loading B and C as well. So it looks like these two values here are relevant to our time variable. So easy thing to do, freeze it. I'm gonna freeze both of them and see what happens. I gotta find the game again thanks to YouTube screwing up. Okay. Go ahead and run the game. We'll turn off the watch point and run the game. And yeah, it looks like our time froze up here. So now we have all the time in the world to mess around. And we can actually change this value and see what happens. So let's go ahead and set it to the max. And see it sets it up there to the short max. Well, off a little bit because the 0, right? Let's go ahead and finish the level here. I haven't explained this game at all, but I might play it tomorrow so I can explain the details. So this bell here, this summons a fairy. We can maybe look into that later. Gives you that 1 up there. All right. So now finish the level. So this value here, the room clear, is this is our time, right? But it's not going down, and it's supposed to be going down to add to the money. So since it's not going down, it's just giving us infinite money, which is not good for a cheat code. We want to be able to finish levels, right? So let's unfreeze this RAM. And then what we're interested in is how how do we, or what actually wrote to this, right? So let's go ahead and do the same thing we did before where we uncheck the read and just have write on. And then we'll figure that out actually right now. As soon as I hit run, it's going to break. If it runs at all, why is it, huh? Oh no. I think the game broke. We'll reset. It's fine. uh, did the emulator break? I hope that's not the case. I want to reset this up. Uh, Whoops. I didn't think that would happen. See my background for a second. Okay. Uh, there we go. Back in game. It happens. At least we know the memory, right? So now we'll set the right value here, or the on right value, and go ahead and start the game, see what sets it. So this, it's just loading 0, 0 into that, so that's just clearing the memory. Not useful. Now here we got, here we're setting from H and L. We can see that HL was set, let me explain this real quick, I suppose. So HL is this register here. It stands for high and low. The way this register and all of the B, C, D, E, all those general purpose registers are set up is that they're both 8-bit and 16-bit registers. So HL is a 16 register. H and L separately are 8-bit registers, but they combine to form the 16-bit register. So if you set to HL here, which this is the one that we're looking at here because it's setting, we can see that HL is 1F40, so this is where we came from. So we set the HL to 1F40, and then if we look at H, we can see that H is the 1F. That's what it's set to the C0 here. And L is the 40, and that's what's going to set to here. If we step 1, we can see that. So that means that this is what wrote to this value initially. If we wanted to change the starting time, we could change this value to something else. But we don't. We want to lock the time. So what we want to look for is not what sets the initial starting time, but what decreases the current time. So we'll go again. Oh, it cleared it again. And reinitialized. Weird. Go. So this is what decreased it. We can tell because if we look at the HL right now, it's 1F 3F. So 40 minus 1 is 3F in hexadecimal. So that's what has decreased the time. And how that actually works. So we'll look at, you can see this is setting from HL. So it modified HL by adding HL with BC. BC is set to -1. So now we get to talk about signed values. So hi, welcome. We're doing nerd magic. So to explain signed values, let's take a look at the Python console again. Now, we have OXFF is the value that it did, right? And the value that it had was OX 1F 3F. So it added those, right? So what happens when you do this? Okay, what happens in hexadecimal when you do this? You can see that the resulting value here. Oh wait, it wasn't. Well, whatever. This still makes sense. So you get 1f, 3f plus 4f's gives you 1, 1f, 3e, right? But BC and all these registers are 16 bits, right? That's 2 bytes. So that's the 1f, 3e. This extra 1 here is discarded. It's what we call this in the biz is an overflow. It's looped around and gone 1 down from its original value. So that's why sign values are represented like this. This value here, FF in signed, is a -1. So when you add, in normal math, when you add -1, it reduces it. So in overflow math, as it were, it overflows it to the next digit up and 1 below, and then cuts that digit off. Hopefully that makes sense. So then what we need to do for our unlimited time is set this value, FFFF, to 0, because, plus 0 means no change. So what we can do for that is we can right-click a line and say Open in Memory Editor. I set a breakpoint there so you can see it in red, but this is the op in binary, or the operation. 1 is the opcode, FFFF is the value. So we need to set these two values to 0. If we go to our cheat editor, that means that we have infinite time 1 and an infinite time 2. If any of you are from GameShark cheating era, I'm sure you've seen codes that have multiple codes. This is why. It's because it covers multiple bytes, and this is what they had to do. So if we click this, we can look at the address down here, 342A. 342A, and then this one, 342B. Set the values to 0. Now, something not special with Game Boy, but with these very retro consoles in general, is they use a system called banking. What that means is that only a portion of the ROM is accessible to the game at any given time. In order to access a different area of ROM, they have to do a bank switch. Yeah, for sure. I didn't either. I gotta learn it, right? So right now this code is in bank 0. That's what this 00 over here on the left means. We only want to change this code when we're in bank 0, but these addresses, as well as GameShark addresses, I think. I'm not totally sure. But wait, actually no. GameShark's only RAM, isn't it? I don't know if they do ROM. Okay, Game Genie codes, which do ROM. What you have to do is, since you can't address the bank in here, you need to go to the compare. So we can set those to equal FFFF. And then what this means is that it will, when it goes to adjust the ROM for infinite time, it will first check that this address here, 342A, at the given bank is equal to FF, or at the current bank, is equal to FF. And if it is, then it will change it to 0 instead. So that's what that does. Now we can try it out. So let's remove that. Let's remove the watch point. Go ahead and hit run. Now it's stuck. It seems like it decreased once, but that's fine. It won't next time. And the time decreased properly that way. So we're good here. But I do want to go over something else. If we go back to that address, which we can do by selecting debugger. We can see here that it checks this address, and if it's not 0, then it jumps past this code entirely, going down to whatever this is, right? This code is also there, so it's basically, it skips decrementing the time if this RAM address is set. So we can reduce this to one code by setting this RAM address, lucky us, right? So if we go to, I show you real quick, this is 0 currently. So if we go to add cheat, we can say C122, set that to a 1. No need for a comparator this time, because in RAM, you just know if it's ROM or RAM based on the address, by the way. You can technically memorize them, or you can be lazy and look here, but it's not so hard to memorize. So let's try out our new cheat. One of the things with cheats like this, where we've noticed something, right? We're not changing ROM. Just this RAM location is used here. We can see that it's actually used elsewhere as well. It's zeroed here. It's used here for something. Does another check for the same sort of thing. And it's used here for something. So this, setting this address clearly has side effects. And we know what they are. So we can play the game to find out. Spoilers, I do know them, and since we're on a time limit, I'm just gonna... The side effect is that it makes you invincible. Poor dog doing his best. So for whatever reason, this is invincibility and infinite time. But yeah, disabling that isn't enough, so we have to actually just go there and edit it real quick to undo it. Was it 122? Okay. Now we can die again. So next up, let's see. Oh, right. The other staple, right? Let's look at infinite lives. So if we hit select here, we can go over to the status pane. Whoops. Stop that. Now, if we look in the tile map here, you can see that the window, this black line here, just shifted over. Now we're in this section here. This 1 is the level. This R is the room, and then the P is your lives. So we'll look at this 2, right? We want to see what assigned this to. It was FFC9. Go back to HRAM. Right here, the 72. Do the same sort of thing. Now that we've done it 3 times, you should be able to remember it, right? Okay. We set the right watch point. Then go ahead and go back. Now, oops, what am I doing? Okay, go back to the screen and see. Oh, it broke. So, I mean, the watch point. That yeah, the game's not broken. Don't worry. uh, so watch point was hit here, and it does the same sort of thing that adds empty, right? So where did it get it? From FF91. So if we look at FF91, that's here. That's HL. Let's put the HL because it was in HL, I guess, or referred to by HL. Oh wait, no, that's FF90. My bad. FF91. Here we go. That makes more sense. It's at 2 right now. So if we then freeze this value, yep. That's why I love using a debugger for this. A lot of people do static disassembly as well and just read the code, but oh my god, this is so much faster. Okay, so now we've frozen the value. Oh, it wasn't that one. It was from 2, wasn't it? I don't know. Wow, what was it? I forgot. Okay, let's do this again. My bad, I'm sorry. Okay. What happened? Did it break again? No. It didn't die at all when I did this yesterday. This game has no save, by the way, if you're wondering why I'm at packet level 1. Okay. Okay. So yeah, it's set from FF91. Yeah. Okay. That's FF91. Uh, FF91 altered. Hmm. Let's look at the reference memory. Not that. I wanted references. Can I not do that? No. Okay. Right. Tools. Run. Uh, Zero that out. Sure is modifying this a lot, huh? Well, that's a read. I don't care about the reads. Yes. I did that accidentally once. It is possible. Okay. So, anyways, from putting this right on here, we can see this value is very busy, it seems. Maybe not good to freeze it. Put it back to right only. Okay. Don't freeze that. Too busy. Uh, Go back, try this again. All right. Oh, my bad. It didn't get A from 9.1, did it? Oh, it did. It did. Okay. So what assigned 9.1? Yes, we want to find that out. Let's try here. This set it. So this first zeroes it. And then rotate some things. Rotate left. Rotate left shifts the bits left, and then the one on this is rotate left with carry through carry rather. So the one on the leftmost position goes into the carry flag, and the carry flag goes into the 0th position, which probably doesn't make a lot of sense. You don't really carry a flag, I guess, but it's not super important for this. Just enough to skim through this, right? Load A0, put that, and we shift that. That HL. Huh. The important thing to us is what the heck. Uh, the heck is going into there initially. I don't think this is relevant actually. Skip. Oh, we weren't in there. Okay, let's do this instead. This is what was called A went into here, right? If we go to the destination, we can see A wasn't used. Shoot. C and B were used though. So C, A is in C. Yeah, okay, it was used. Yay. Look at this FFC8 instead. That's the eventual input to this. So FFC8 is right here. Go ahead and freeze that value. It's at 3 right now. We have 2 lives. Or not freeze. Do we want to freeze? No, we'll just edit it. Okay, so let's disable this, toggle it off. Go ahead and play. Back up. We'll go ahead and set this to a different number. Set it to 8. It's not changing. That's good. Go back over. Now we have 7 lives. So this is another off by 1 situation where we have +1 of the value that is shown on screen. But it does appear to be the lives. The reason for why this is a +1 is because it can show a 0. However, the game code wants to use 0 to see if you've died. So when it does a -1, it checks if the result is 0 or not, and if it's 0, then it's like you're dead, or you got a game over, right? So that's just an easy way to do that. In order to do that, it does that dec A before adding the 70 to it. Okay, now that we figured that out, we can let's see how big this goes. Set it to FF. So obviously for the cheat, we want the biggest number, right? Doesn't look right. So it seems to have 2 digits. It definitely doesn't support 3. So what we want then is the hex value for 99, which is 63, and we add 1 like it wants. So let's do 64. It changed back. Why? Why is it changing back? Oh no. Okay. Do 64 and then we'll freeze it. Can't tell me what to do. Emulicious is glitching again, isn't it? Isn't it? Okay. I'm going to set the cheat. So we don't forget the location. FF C9 64. As soon as I do something cursed, it's screwing up the emulator. I don't know what's up with this. Huh, now we have PE. How strange. Oh, I set the wrong value, didn't I? I was supposed to set this value C8. 64. Wait, freeze that. Cheat. C8. There we go. 99 lives. We did it. Sweet. Oh. So we can go ahead and kill ourselves and see that that's the case still. It says 98, but what's the back button? Oh, level select. If we go to level select and then go back, it resets. So I'd say that's pretty good. You wanted to change the level. We found the room earlier, right? So we can go ahead and find the level and see what happens. RAM search. So set that to 1, unsigned, reset. We want a constant of the room was off by 1, so we can assume that this is also off by 1. Right, so we'll put 0. And go to the level select. Go to level 2. And now we can say 1. These two are not relevant. Of course you can't delete the last one, why would you? Okay, there we go. So now we have 2 options here. This is right next to our room address. So it's probably this one. If we go to that, can I open that? Yeah, okay, select a memory editor. So let's go ahead and open this, or set this rather, to say 3. It changed our, did it change our room? I didn't change our room, did it? Oh, 4? Maybe it doesn't update. But we can test this another way, so let's freeze that. Go ahead and go there. Not very frozen, is it? Went back to 0. I'm starting to hate this emulator. Why was this fine last night and now it's just a constant state of cruft? Oh, you can see it flash the 5 there. So it did take us to level 5. The emulator just is being really freaking annoying about it. So if we set this to something that's not allowed, it takes us to the shop. Well, that's fun. See where else we can go. Oh, level S, room 1. Oh, okay. This is a boss? Run away. Let's see how bad I actually am at this game. I haven't played that far. Yeah, pretty interesting. Okay, so we want the fire to fall in there and then do that. And then we don't hit it again. Uh, yeah, we'll want that there. Okay. I guess these are real levels though. It seems like a real level. I have to go over there. Oh man. How did I do this? Okay, and we go back down here and then like that. Okay. Ah. Oh. Interesting, interesting. And it just went straight to the next level. It didn't even take us back to the level select. Fascinating. Okay, let's go back to 0 for a sec. All right, and now we're going to change this to another one and see where else we can go. Come on, freeze the damn value. Level blank, room 1. All right. Does it give us something glitched? Wow, yes it did. Oh no, I spawned in a block. Huh. Hmm. So yes, you could do stuff like this too. Extra rooms. Can't even win him. I kind of like just jumping to the shop though. That's pretty sweet. I'm gonna store that one in the cheats. Go to shop. That was 05. Okay. We can see if the next one's any better, huh? Room 2. Didn't spawn us off screen that time. But I won immediately. Hmm. And we've jumped to A. Oh no. Okay. Uh, well, with that fun stuff, I think I'm going to end it here. Hope you guys learned a thing or two. I will probably be doing, yep, Shadow Realm. I will probably be doing streams similar to this more in the future. It might not be looking for cheats, and we might be doing like actual reverse engineering, like learning how things work or doing translations or something. Uh, but yeah, it was good for a first stream. Shows you the basic principles and stuff like that. So um, yeah, like and subscribe. Okay, have a good one. Bye bye.